So this is going on page 52. We're going to look at extrema on an interval. So extrema being your maximums and minimums. And on intervals, not looking at the entire function as one. Okay, so our definition of extrema. So let f. Hello. Okay, thank you. Let f be defined on an interval I. So this capital I is just an interval containing c. This c is some x value. Okay, so this is just an x value. If f of c, so this right here, this is just a y value, is the minimum. If f of c is less than f of x, so what that means is that what this right here is saying is that the y value is below the entire function, the rest of the function. The rest of the function. And that means that it is the smallest value hence minimum, right? And so this is on an interval, so not the rest of the function on the interval is what it means, the smallest value on the interval. Minimum, maximum, those aren't brand new concepts for you, but looking at them on intervals is just a little bit different. F of c is the maximum of f on the interval if it's greater than the function, so the biggest number over the entire interval. Okay, so the minimum and maximum of a function on an interval are the extreme values, or extrema, that's how you say it plural. Okay, the minimum and maximum of a function on an interval are also called absolute minimum or absolute maximum or global. So absolute and global, exact same thing, just like relative and local are the same thing when you're talking about them that way. Okay, so on to relative extrema. So if there is an open interval containing c, which remember is just some x value, on which f of c is a maximum, then it's called a relative maximum or a relative minimum. There's an open interval, again, open interval containing c. This is important. I'll show you why that whole open interval there is important. Where f of c is a minimum, then it's called the relative minimum, or it says relative minimum. Oh, I thought it said relative minimum or relative minimum. Relative minimum or local minimum. They're the same thing, relative and local. And so you have the value, the maximum minimum value are the y values, the location is the x value. It's kind of important to keep that part straight as well. So when we look at this function here, it says in the figure at the right on the interval, and this is a closed interval, okay, so closed interval, the absolute maximum or minimum, so absolutes, that's the biggest and smallest values here and here, right, and I can't make points on this stupid board. So the absolute maximum value, it says f has an absolute maximum at, that's the location, it is at x equals 4, but the value is 21. Okay, so it's at, the maximum value is 21, it is at x equals 4. Okay, so make sure that we're saying those things correctly there. Absolute minimum at x equals -2, and it is -15. When we're talking relative, remember that had this little notation here of open intervals. So open intervals means we're not including the endpoints. So your relatives, even though absolute, one of the things we learned last year is your absolute maximums and minimums are also relative maximums and minimums, and that is still a true statement. But here, when you're looking at relative, we're looking at open intervals, so we don't include the endpoints. But if we had a bunch of, little back and forth, we could count them more than, count more than one of them. But my relative Max and mins are here. So my relative maximum on this open interval is here at x equals 0, and it is 5. Then my relative minimum is at x equals 2, and it is 1. So one of the reasons we need to look at this is because we are looking for our critical values. This is how we find critical values. And if you take the derivative, we get the slope, right? So at our relative maximum and minimum values, what is the slope of the tangent line? 0, okay? So when the slope of the tangent line is 0, that's because we have a horizontal line right there. And that's how we know that we have maximums and minimums there. So if we're looking at the derivative, or we have the derivative, and we know that the derivative is 0, that means the slope of the tangent line is 0, so it's a horizontal line that indicates a maximum and minimum for our original function. Okay, that's what we're looking at here. And I can tell by the looks of all your little sweet little faces, this weather has got you kind of down, and thank God it's Friday. You all just look like it is the worst day ever. Like, I just see a bunch of little sad, depressed faces out here. No depression. We shouldn't be sad. We're doing calculus. This is fun, right? Smiles. See, now we have smiles. Woohoo! Okay, that's what we needed to hear. Y'all just all look like, oh my God. Okay. It's kind of funny, but not funny. It looks really pathetic. Y'all just look pathetic today, as a whole. Every single one of you. It's the looks on your faces. You're just like, this is terrible. Okay. All right. Now, okay. So critical numbers. Remember, I just said we're looking for critical points. So our definition of a critical number and a critical point. Let f be defined at c. Remember, that's just an x value. So if f prime of c equals 0, or if f is not differentiable. So if f is not differentiable at c, that means that f prime of c does not exist. Okay, so either if it equals 0 or if it does not exist, then it is a critical number of f. And the point c, f of c, is then a critical point. Okay, one of the things that we're looking for. We good with that? Okay, so let's draw a bunch of cute little graphs here. So we are going to, says draw a continuous function on the closed interval from a to b. We don't know where a and b is. We'll just kind of put them in the same spot each time. It'll just be a little kind of helpful there, like a and b here. That looks good. F is not differential. Oh, I'm sorry. I went back up there. With characteristics for each of the situations below. So here it says we have the max at an endpoint and a minimum at an endpoint. So we could draw something. So let's say that this is A, this is B, and then we could draw something like this. So here we have a max at this endpoint and a minimum. Sorry, I have to use the dots because I can't actually draw points. So we have a max at an endpoint and a min at an endpoint. Okay, that's something that could happen. That's one thing that we could have, that what it would look like. All right. So then let's have a max not at an endpoint and a minimum at an endpoint. A and B again. A and B. So I want my maximum not at an endpoint, but the minimum at an endpoint. I could do something like this, where then there's a point and there's a point. So my maximum is actually right there, and my minimum point is there. Okay, we okay with that? So that's an absolute max right there for that interval. All right, minimum not at an endpoint, and max. Oh, goodness, that's why I didn't do it that way. Minimum not at an endpoint, max not at an endpoint. So we could do something like this, maybe. Oh, wait, is and, min not at an, thank you. It would help if I could read, which apparently I can't. So min not at an endpoint, max at an endpoint. Okay, so it's like this, something like that. Y'all agree with that? Thank you. Reading can be difficult sometimes. Max not at an endpoint and minimum not at an endpoint. That's what I was trying to do over there. Something like that. And you're not always going to have the graph to look at to figure this stuff out, but just see how these things could work. Max not at an endpoint, and f is not differentiable at the max. So what's something that we could do? It's probably the easiest thing to draw where it's not differentiable. Sharp point, maybe? I mean, it's a matter of opinion which one's the easiest to draw, but I think that works. So if I want my max not at an endpoint, it doesn't really say anything about the minimum, and it also can't be differentiable at the max, then it could look something like that, right? All right, so a max not at an endpoint or a critical point, and a min not at an endpoint or a critical point. That is not possible. Not possible. Okay. All right, everybody okay with all that? All right, I'll take that as a yes. All right, so extreme value theorem. So we had IVT and MVT, now we have EVT. Extreme value theorem says that if f is continuous on a closed interval, which all the VT ones have had to be continuous, right? Then f attains, fancy way to say it, an absolute maximum value f of c and an absolute minimum value f of d, because they're just different numbers, c and d, they're just x values, for some numbers c and d on that interval. Okay, so if it's continuous, we have to have an absolute max and min, either on the endpoints or some other point in that function. Okay, so guidelines for finding this on a closed interval. Here's what we are doing. We are calling this the candidates test. I'm going to use this kind of, and the candidates test is one of those where it's very specific about what you have to write down. And yes, sometimes you can leave things off, but then it makes it more complicated because you have to write more words. So it's kind of best, in my opinion, if you just always put everything in there, then you don't have to worry about being specific about things. It makes everything, working it out a little bit easier. Okay, so we're going to find the extrema of a continuous function on a closed interval, we're going to use the following steps. We're going to find the derivative. We know how to do that. And the critical numbers of f on the interval a to b. So that means we're going to set both the numerator and denominator of f prime of x equal to 0. That's how we find them. We find the derivative and then set them equal to 0. The reason we're doing that is because if we set the numerator equal to 0 and it's the derivative, we get every time that the derivative is 0, that gives us our horizontal asymptotes, right? So that tells us if we have max and min points, or if it doesn't exist, and that's why we do the denominator, because that would make, if it's irrational, we put the denominator in there, and that gives us where our vertical asymptotes are, where it doesn't exist, okay? And then the endpoints, we evaluate f at each critical number, evaluate f at each endpoint, and the least of these values is the minimum, the greatest is the maximum. Remember to discern, there's some more fancy words in here, decide the difference between where the max or min occurs as opposed to what it is. Okay, the where is the x value, the what is the y value. So make sure you keep that straight. Anytime we're talking about location, it is at an x value. The value itself is the y value. And that's true for everything, so it's not like it changes between the things that we're doing. Okay. So we're going to find the absolute minimum, maximum and minimum of f on the given closed interval and state where these values occur. Okay, so the first thing that we do is we're going to take the derivative, which is something we can handle, right? This is fairly simple. So f prime of x is equal to 6x minus 24. Y'all agree with that? Okay. So then we're going to take this, we take the derivative, and we set it equal to 0, and we solve for x. So I set it equal to 0. That's equal to 6x minus 24. So 24 equals 6x, and x equals 4. Okay. So this is called the candidates test because we have the candidates for what can actually be our maximum points. So we're going to do a little t-chart here. And notice that we found the derivative, but this t-chart is x and f of x. This is giving us, when we take the derivative and set it equal to 0, it gives us one of the candidates. Two of the candidates are always the endpoints. So -1 is one candidate, and then whatever my x values are, which is just 4 in this case, and then the other endpoint. Okay. Everybody okay with that? Then we evaluate each of them at f. So f of -1, not f prime, but f. Okay. So f of -1, this would give me, let's see, -1 squared is 1, so this is 3. Then -1 times -24, that'd be plus 24, and then minus 1. Right? So if I put all that together, what do I get? 26. So this is 26. Then I'm going to do f of 4. And if you have to write more stuff down, that's fine. So 4 squared, when I substitute it in here, is 16. 16 times 3 is 48. And then positive 4 times 24, what is that? I'm sorry, positive 4 times -24. So 2 times 24 is 48. And then if I double that, I get 96. Right? So that's -96. And then minus 1. And when I think about it that way, 2 times 24 is 48, and 48 times 2 is 96. So very easily, 48 minus 96 is -48, right? Subtract 1 more, I get -49. Okay. Then I do f of 5. So 5 squared is 25 times 3, 75. 5 times 24, -120. Good. And then minus 1. So that'd be what? -45, -46. You'll agree with that? All right, so remember, these 3 x values were the candidates for the location of our maximums and minimums on this interval. And so I can tell you that the largest value is 26 and the smallest value is -49. Would you agree with that? Okay, so then to answer the question, we would say the max is, what is the max? 26, because it's the value. Max is 26 at x equals -1. We agree with that? And then the min is what? -49 at x equals 4. And that's all you really have to write. You don't have to say by EBT or anything like that. Your candidates test and actually using all of the specific, all of the correct candidates, that is your work, that is your justification, and then you're just kind of finishing it up with that. So it's not something you have to write a big sentence about or anything. We okay with that? And we're going to apply the candidates test are going to apply to certain things that we do. It's not that difficult. It's not that big of a deal. We just got to make sure that we remember to use the endpoints and all of the zeros from the derivative. Okay? What questions you got? Okay. So let's look at B. We're going to do f prime of x. It's going to give me 18x squared minus 24x cubed. And then that's it, right? Okay, so we're going to set that. So set that equal to 0 and find your x values. Did any of you do the next step by moving something over to the other side? Don't do that, right? We don't do that. We did that on that one over there because it was linear. What do you have to do here? Factor. Do you have a GCF? Yes, make sure you use it. You get x equals 0 and x equals what? 3/4. What questions we got at this point? Are we all good here? Okay, don't start doing weird things. You know how to solve these things. We knew here it was fine to go ahead and, move that over. Don't just automatically move it over to the other side. If you need to factor something out, factor it, and then you use your zero product property, right, to find these two values here. Okay, so that means on my candidates test, I actually have 4 things this time. Okay, I'm going to have x and f of x. So I use my endpoint, -1. Then I have 0. Then I have 3/4. And then I have 2. I think I wrote too big on the other one. So I keep trying to scroll. Well, I don't guess I need to be able to see that. So then we're going to find all of our values here. Now let's talk about how we can work smarter, not harder on some of this stuff. So when I want to find f of -1, well, -1 cubed is -1, so that's -6. -1 to the 4th is 1, so that's another -6, and then +5. Right? That's -12 plus 5 gives me what? -7. Okay. F of 0, that's going to be 5. Just straight up 5, no big deal. F of 3/4, this one gets a little bit yucky, right? So we're going to have 6 times 3/4 cubed minus 6 times 3/4 to the 4th plus 5. Okay, pause on that one for just a minute. Okay, and we're going to do the f of 2, and then we'll talk about why we don't really have to work that one out, because we can use some logic and write some other stuff down here. Then we have f of 2 and f of 2. Let's see, 2 cubed is what? 8. And so this is 6 times 8, which is 48. I guess I could have written that, but I already wrote that, so 48 is fine. Minus, what's 2 to the 4th? 16. 6 times 16. Okay, and then plus 5. Plus 5. All right. Then let's talk about these values here. Look at these two right here. Of these two, which one is smaller? The first one or the second one, I guess, put it that way. Which, if I was to actually multiply this stuff out without multiplying it out, which one would be a smaller value, the first one or the second one? Actually, the second one, because when I take a fraction to a power, it gets smaller and smaller, right? So what I know from this is that these two together give me some positive number, right? I don't know what it is, but it's some positive number. Would you agree with that? Okay, so it's some positive number plus 5. So that means that this has to be greater than 5, right? So whatever it is greater than 5. Okay? You with me on that? What's the question? Well, since it's smaller, since this value is smaller, since I'm subtracting some number minus a smaller number, then it makes it positive. Are you with me on that? Okay. And since they're so similar to each other, you can know for sure that it has to be smaller because it's almost the same thing, right? It looks the same. All right. So then here, well, if 6 times 8 is 48, I'm kind of glad I wrote it down that way. Isn't 16 just 2 times 8? So this is 6 times 8 times 2. So what would this have to be? 96, 2 times 48, right? So 48 minus 96 plus 5, yeah, negative 48 plus 5, even if I don't do all the math, is that less than negative 7? Yes. So that is less than negative 7. Now, if we look at what the question actually asks, oh, it does say to actually find them. Dang it. Well, sorry. We do have to actually find them. No, because when I was talking with Mr. Ackerman about this, he was like this, and this is how we can do it. So sometimes it just asks you where. Okay, so we're going to pretend on this one it just asks you where, because sometimes it does, because nobody really, I mean, yes, are we capable of actually doing this math? 100%. But does that get yucky? Are we testing your fractions and stupid stuff like that? So in this one, we're just going to answer it that way because, again, a lot of times it's the where. So we can, on this one, we're going to not cheat a little bit, but we're going to answer it differently, even though it says it that way. We're going to say the max value, the max is at what point? At 3/4, x equals 3/4. Yes, because this is greater than 5. Okay, so that is at x equals 3/4. And the minimum value is at what? X equals 2. Okay. Sometimes we need to know what when they end up yucky like this, and you can use this kind of process without actually doing the math, all they're going to ask you for is the x. Okay, that comes up some. And then sometimes we need the value. Most of the time it is where is it, is the x value. Okay, we good with that? All right. So I want you to find the derivative on C. Do you agree with me up to that point? Okay, now do you remember where we said we have to set the numerator equal to 0 and the denominator equal to 0? That means we have to actually have one numerator and one denominator, so we need to combine those fractions, right? It's not that bad. Don't be like that, okay? So f prime of x is equal to, so we're going to have some fraction. What is my denominator going to be? We got to get a common denominator. Let's not make this hard. We'll use this one, right? Yeah, x to the 1/3 power. If that's my denominator, this first numerator is totally fine, right? But this negative 2 has to be multiplied by x to the 1/3 over x to the 1/3, right? Which makes that second one turn into 2x to the 1/3 power. Okay. Everybody okay with that? Right, so here's what's happening. F prime of x equals 0 when the numerator equals 0, so that's 2 minus 2x to the 1/3 equals 0. Okay, that's when the derivative will equal 0. And so we want to solve that and figure out when that is. So am I factoring anything out here? I mean, technically I could factor it out, but are we really factoring it out? We're not really factoring it out, right? So I can move that over, so I'm going to get 2 equals 2x to the 1/3 power. What can I divide both sides by? 2. Okay, so let me give you this other little hint, just in case. Because yes, I could have done that one by factoring as well. On this question right here, if I had moved that 18x squared over and then divided both sides by something, if I'm going to divide a variable out, that's when I know I need to stop and I should have factored. When I move it over and I'm going to divide by both sides, if I'm not dividing by a variable, then it's fine for me to do it that way. That's how you can know for sure whether you're going down the right road, even when you have choices. Okay, so that means that I get 1 equal, and what's another way to write x to the 1/3 power? Cube root. So this is really, and you don't necessarily have to write it that way if you know what it is. That's 1 equals the cube root of x. So how do I undo a cube root? I cube it. So if I cube both sides, what does x equal? 1. That's one of my candidates. Okay. Then f prime of x does not exist when the denominator equals 0, when x to the 1/3 equals 0, right? That's why we set the numerator and denominator. So numerator equal to 0, the whole function's equal to 0. When the denominator is equal to 0, that's when that function does not exist, okay? And then if x to the 1/3 equals 0, what does x equal? 0, okay? So there's my other candidate. And I don't know how much, were y'all running out of room? You might be. I kind of feel like you might be, because I feel like I should have already, but I have endless room, and I know that you don't. We'll just do the best we can to fit this on here. All right, so then x and f of x. What's my first candidate? -1, good. Then what's my next one? 0, then 1, then 8. So I have 4 candidates. So go ahead and find those 4 values. And these you can find, and it's not. So we're setting them both. We set the numerator equal to 0 and the denominator equal to 0. But the derivative itself, the way you make this function equal 0 is when the numerator is 0. When the denominator is 0, that's where you get a vertical asymptote, and it doesn't exist. Okay, so that's why we're looking at when it equals 0 and when it doesn't exist. That's a good question. Did that make sense? Do I need to say that again? Okay, I'll say it again. I'm sorry. So on all the other ones, we just set it equal to 0, right? And yes, if I set this right here equal to 0, that's basically all that's going to give me is when is the function equal to 0. Well, this is a rational function. For rational functions, when the numerator equals 0, the function equals 0. When the denominator equals 0, that's when you get your vertical asymptote and when the function doesn't exist. Okay? So we're still setting them both equal to 0, the numerator and the denominator. So the function equals 0 when the numerator equals 0, that's what we mean here, and the function doesn't exist when the denominator equals 0. And we have to consider both. Okay? See? All you gotta do is ask me to re-explain it. That's why I'm here. We good? Think Carolina understands? Oh, okay. That was a little harsh, but okay. You had that coming. All right. Sure. Did it just sink in while you're sleeping? You got it? Okay. All right. We finding these? You got this. Come on. everything you missed, girl. Okay. Oh, do we need to talk about how to do it? Okay. That's fine. Again, that's why I'm here. All right, so f of -1. When you have something to the 2/3 power, you are squaring it and taking the cube root, and it doesn't matter what order you do it in. Okay? So if I'm going to put in a -1, so x to the -1 to the 2/3 power, I'd square it first and get a +1, then I'd take the cube root and I get 1, so that's just 3. And then that would be +2 + 1, right? Okay. So then I get 6. So when I put in 0, that's super easy. What do we get? 1. Okay. When I put in 1, that's actually super easy also because the signs aren't even going to change, right? So f of 1 is going to be 3 minus 2 plus 1. We agree with that? So is that going to be 2? And then f of 8. So here's where the order in which you do it, I think, would make a difference for me anyway. Here, let's just write this down. We got 8 to the 2/3 power. Right, so this right here. I can either square it and then take the cube root, or I can take the cube root and then square it. Now, it's a matter of opinion, but personally, I think it would be easier if we took the cube root and then squared it, right? So the cube root of 8 is 2. 2 squared is 4. Okay, so that's going to give me 12. Not equals. So this actually becomes 12, right? And then 8 times a -2 is a -16 plus 1. So what is that? -3. Do we agree with those? Okay. Because again, I could have squared it, gotten 64. The cube root of 64 is 4, but you're more likely to know the smaller numbers. All right. So then, if you don't have room to write out what the max and mins are, that's okay because you can figure them out, right? You would know what to write at this point. We good on that? Okay. So the only homework I'm giving you on this right now is for you to finish to do D. You can start that now. You got 5 minutes. Do it and have it done before Monday and come with questions. Mm-hmm. Yes, so basically what I did here is I had 3 times 8 to the 2/3, so that's the cube root of 8, and I could either have the squared on the inside or the outside, so this is the order I did it in. So I took the cube root and got 2, 2 squared is 4, and then times 3. Okay, does that make sense? Okay, good deal. Thank you for asking. Take the derivative. Do it now. Yes, you do. Shut your mouth. Okay, let me remind you all something. All right, let's back up a little bit. See, this is why I'm not just doing it all, because I need to know where your questions are on this stuff. Everywhere. I would rewrite this as f of, well, if I had a pen. Okay. I would rewrite this as f of x equals the sine of x squared plus cosine of x. Remember how this is how we write it, but this is really what's happening. And when you're taking the derivative, it makes much more sense when you're doing it if you write it like this, because then what rule do you have to use here? Chain rule, exactly. Oh, makes you shiver. Okay. I mean, you don't necessarily have to rewrite it. You can just know what it's supposed to be, but that doesn't always work out too well for most people. So let's all get the derivative. Do it now. Okay. I'll make sure we have the derivative right before we leave, and then you can finish up the rest, but I want you to at least try it first. I'm going to write it down, but don't look at mine until yours is done. Once you have tried it, then you can look at mine and see if we agree. Multiply, keep the inside, subtract 1. That's that. Derivative of the inside. Then when you set it equal to 0, what are you going to have to do? Factor. Set it equal to 0 and factor. And use your brain cells. You got this. You got this.